All right. So inverse kinematics. We're talking about this today because I consider it to be one of the Roblox developer rites of passage. It's a common problem that people need solved, and so yeah. I figure it'd be worth giving a talk on. Okay, so the problem statement here is we're dealing with uh, robotic arms. So think of we have a robotic arm. We start it at the shoulder, and we have uh, some arm segments, and then it ends here at, I guess, the hand. And if we know the lengths of each of these arms, let's do. So if we know the first length, we know these, and we know the angles between them, then it's not too hard to start at the shoulder and then figure out where the end is, where the end of the arm is. But what we're concerned with is actually if you don't have these angles, but you do have the end of the arm, how do you determine the angles between the arms? So if we go in the forward direction, that's called forward kinematics. This is trying to find where the hand is placed. But if we go in the backwards direction, that's called inverse kinematics. So we have the shoulder, we have the arm lengths, and we have the hand, and we need to determine how we want to place the arms. So one use case for this is in actual robots. So in this case, I mean, it's probably much more complicated, on robots like this, but the principle is there that you know where the base of the robot is, you know the arm lengths, and you know where it wants to be, and you need to determine where does this elbow go. So that's the principle there. But in game development, it's actually a bit easier because in game development we want to do this on characters. So we want to do this for the character arms and legs. And here's an example from Matthias, who's in this server. He made this really cool spider.
That's amazing.
Yeah. So in this case, what we have is our inputs are let me try. Yeah, there we go. So the inputs are like the shoulders and the where the feet go, and we need to determine how do the legs get placed in that system. Right. Okay. So what's interesting about this problem is there was kind of a fad a few years ago doing inverse kinematics among Roblox developers, but it became topical recently because there's currently a bug bounty for the Nexus VR character system. So I know, Dan, you use VR, but I don't know if you've noticed this problem before.
I saw this in my inbox a few days ago. Yeah, I didn't realize this is why you chose to speak on this, or maybe that contributed, but I thought it was a very strange coincidence.
Yeah. There's been a few different parties working on claiming the bug, claiming the bounty. Uh, the person who is closest right now he's not in the server, but he's a kind of a math friend of some people. Uh, Not this Ben, but another Ben. So here's what he has right now. So this looks pretty good. I can, yeah. So yeah, him and I actually came up kind of with the same idea, but he has actually implemented it faster. So we'll see who wins there. But anyway, so in games, we can model arms pretty simply as just an upper arm and a lower arm, and that makes the calculations quite simple. Because if we look up at this general case that I described, you're going to need some kind of iterative method to do this. A bit more complicated algorithm. Whereas in the 2D, in the two, sorry, the upper arm, you have when you model your arm as two lengths, it's quite simple. So let's draw a diagram. we have the shoulder, we have the wrist, and this is the upper arm and the lower arm. So let me label these. And our task is to determine where do we place this elbow. And the first thing, okay, what I thought was really cool about this problem when I first approached it, must have been 5 years or so now, is how geometric it is. So the way to determine where this elbow goes is to realize that this upper arm here, it can rotate anywhere around the shoulder. And if we trace out its rotation, what we get is a circle. So this arm can be placed anywhere around this circle. And then we can do the same thing for the lower arm. So the lower arm can have this rotation. And where the elbow gets placed is where these two circles intersect. So in the 2D case, we have two possible intersections. We have the one up here and the one at the bottom. And if we want to take this into 3 dimensions, instead of having two possible locations for the elbow, we actually get infinitely many possibilities. Because if you intersect in the 3D case, we're intersecting two spheres. Spheres intersect at a circle. So we have a whole circle of possibilities for where the elbow can go. Right, let me clean up this diagram so we can actually do a bit of math on it. Okay, so this is what we have. We have the position of the shoulder, the position of the wrist. Oh, and another thing we have is the arms. So we have the lengths of the arms. So we'll just consider these to be the lengths of the arms. So we don't know where we want to put them yet. Actually, let me back up. Let me just add those to the diagram. Okay, this is what we have. So we want to determine from the information we're given where the elbow is located. And so I'll tell you, these are our inputs. The position of the shoulder, position of the wrist, and then the lengths of the arms. So I'm going to step away. I'm going to go find my water bottle, but I'm going to give you like 2 minutes to think about this. How do we, given this information, how do we find the elbow? So I'll be right back. Okay. That wasn't 2 minutes, but does anybody have any ideas? Okay. In that case, I will just proceed. So the way we're going to solve this is with a formula called the law of cosines. And the law of cosine says, so let's draw a triangle. So the law of cosine says if we're given a triangle and we have the side lengths and we want to determine, we have the side lengths and we want uh, an angle here. So here's how they're related. Okay. So the information that we have is if we map this onto our problem is the upper arm, that's going to be A, the lower arm, that length is going to be B, and then C is going to be the distance, or actually, I think I labeled these wrong. This is A, this is C, and then B is the distance between the shoulder and the wrist. And we want to find this angle, because with this angle, it'll help us to find the elbow. So let's manipulate this formula a little bit. Let's square both sides. And let's see, we're trying to find gamma, so let's subtract a squared and b squared. And then we'll divide by negative 2ab. Okay, and then we can actually stop here. So we don't need the exact value of gamma because, where am I looking? Oh yeah, I do have separate. Yes. Right. So the elbow position, I wish I'd written this on the upper elbow, but this is going to be circle math. What is this? It's going to be this vector plus this vector.
Which one are you
Right,
asking about?
I'm trying to remember how to get this elbow.
Well, so it's what you're adding is b cosine gamma plus comma. A cosine gamma and a sine gamma, negative a sine gamma.
Right. Yeah, that makes sense. Okay, so yes. So the elbow is starting at A, and we want.
I guess you didn't. You didn't introduce a name for that position at the center of the circle. I guess you probably want that now, right?
Right. Yeah. So we'll call that. I think in my code I called that the plane of intersection. We can call it. No, we already have C. Sure, we can use P. So we're going to start the elbow.
Oh, I meant the. I guess it's the shoulder, unless you want that to be the origin. Maybe that's convenient anyway. Why not, right?
Oh, yeah, I'll go with shoulder.
Mm-hmm.
Right, so we're going to start at the shoulder, and it's going to be. The reason I'm struggling is because we actually, and eventually in our code, we're actually not going to need this. What we really only need is this height here.
Right.
This height. So okay, maybe we'll just.
So it's a
remember that
it's a cosine gamma, comma minus a sine gamma. Is the vector you want to add there? Yeah.
A cosine. Okay. I'm not. Because A is the side length. Okay, we don't need it.
Mm-hmm.
This is really what we need here. And then eventually we're also going to need sine of gamma, which is by Pythagorean theorem, it's going to be
cosine squared.
Yeah. Okay. That's what we need. That's
right.
Okay, let's
Sorry to be a pain, but so if you write the gamma squared like that, it looks like it's cosine of gamma squared. But what you mean is cosine of gamma all squared. Right?
Right, you're right. Okay, I'd say that's enough math introduction, and we should start coding. Cool. So yeah, I've done some preliminary work to set up our guy here. He has an arm. This is his shoulder, his wrist, and then the upper and the lower arms. Right. So some stuff off the bat, just kind of boilerplate. We have some variables for the arm, the shoulder, the wrist. Gizmo. This is for visualizing things like vectors and whatnot. That'll be helpful for seeing what we're doing. And then we also want to be running some code on heartbeat because we want to update every frame. So let's think about our inputs for the problem. Let's see, we want the position of the shoulder. We want the position of the wrist, and then the lengths of the upper and lower arm. Okay, and then some things that'll be helpful for us. So these will be derived from the input is the vector from the shoulder to the wrist. Also that distance, so the magnitude of that vector. And then we also want the total arm span. So the arm span is summing the length of the upper arm and the lower arm.
We didn't use that
Okay,
in the math just now. Why is that necessary?
which one?
The arm span.
Oh, yeah, okay, this is something I forgot to explain. So there are a few different scenarios for how our circles can intersect.
Oh, right.
So there's like the good case, which we like where they do intersect and we actually have elbow positions. But then there's also the case where the wrist is too far away, or they can be touching at one point, or it can be completely inside of the shoulder. So this is just kind of nonsense. Your arm would be completely broken. In this case here, usually what people will do is the arm just kind of does its best to like be outstretched in the direction of the wrist, but not actually touch it. Actually, so it's the opposite in the VR character for Nexus VR because we always want the arms to be touching where the VR controllers are. So actually, we attach the arm to the wrist, and then it's broken off from the shoulder. Okay, so the reason we wanted this distance is so we can determine which scenario we're in. Right. So that's actually what we're going to do immediately. So if the distance to the wrist is greater than or equal to the arm span, so that accounts for this case here in the bottom right, or well, these two cases here on the right. And in this case, the right. So in like the good case, we were looking for the center of this line here between the elbows, but that kind of doesn't exist in these two cases. So we just consider it to be um, here. So we'll call that the center And the center is going to be starting at the shoulder. We're going to then move in the direction of the wrist by the length of the upper arm.
This is proposition 20 of Euclid, right? Dis to wrist should be greater than arm span if the triangle is not degenerate.
Thank you. Yeah. Right. And then, okay. Also, in this case, what we would usually call like this radius here. Or okay, I'm calling it a radius because in 3D, I'm drawing it in 2D, but really in 3D we got a circle of intersection. And so that red line that I've drawn on the left side in the 2D case is really the radius of a circle in the 3D case. So in this kind of degenerate case here, the radius is just 0. Okay, so that's the case where the wrist is too far away. But then let's get to the more interesting case of what if we can actually reach it. So in this case, we use our law of cosines. We're going to use this formula here to find cosine of gamma. And okay, c squared. C squared is the lower arm length. A squared is the upper arm length, and then b squared is the distance to the wrist. All right, so this is going to look like this. Right, c squared, right, and the upper arm length. And then we divide by negative 2ab. Right, so that's going to be negative 2 times the upper arm length times the distance to the wrist. And then we also wanted sine gamma. So sine gamma we did using the Pythagorean theorem here. Right, and then the last thing we need is, okay, this diagram is getting quite messy. The last thing we need is this length here. I've called it the adjacent, just kind of, opposite adjacent sides. And that is cosine theta times A, or the upper arm length. I said theta, gamma. Okay, and then we're almost there. So now we can find this position in the center. That's going to start at the shoulder. We're going to move in the direction of the wrist by the length of the adjacent side. And lastly, we also need the radius of the circle. And that's going to be sine of gamma times the upper arm length, so A. Okay, so we're very close now. So what we want to do is, right, okay, maybe I'll just code it and then explain it after I do it. So this circle we have positioned at the center here, and we're looking in the direction of the wrist. Maybe it would help if we visualize what we're doing. So let's draw a circle. Right. Okay, so we can see here this is our circle of intersection, and the circle of intersection is centered at that center position, and it's a C frame looking from the center to the wrist. And then, oh, you actually can't see it, but at the bottom here, that's where we've placed our elbow. So the way I place the elbow, where's the script? So the way I place the elbow, it starts at the center of the circle, and then we move down by the up vector of the circle. So I can show you what the up vector looks like.
What does one have to do to set up Gizmo? You have this module script inside something, or
Yeah, so there's a plugin to help install Gizmo because uh, it has like attributes under it, and I don't know if those save if you put it in the toolbox. I don't know. For some reason, there's a plugin to install it. I actually have a modified version of Gizmo. That's how I'm doing the circle. Oops. Yeah, that the circle's not in Gizmo. I had to add that. Um, okay, you can't see what I wanted you to see. Where did my code go? Oh, I'm looking at the wrong one. Uh, why didn't that work?
you need to add the up vector to the position,
Oh, you're right. Well, okay, it's actually
or is it? If it's array, you're probably giving it
yeah,
start and
it's
stop
Ray.
positions.
Am I just not seeing it? Okay.
What happens if you pass in the position plus the up vector rather than just up vector?
Yeah. I think for that it should be draw vector or draw arrow. Oh, it's there. It's inside of the circle. Okay, let me make that transparent. Okay, there we go. So the reason we're using a C frame, I've lost it now. The reason we're using a C frame for the circle is that we get these nice properties of where a C frame has an up vector defined and a right vector defined. I didn't draw up the right vector. Well, it points to the right. So what I'm doing for
How does the C-frame math work? I mean, how does it choose up vectors if you just give it look at? I never looked at
right.
this.
So by default, the up vector for the C frame is the y-axis. But we can actually do better, and this is getting a little ahead of what I wanted to show. Uh, but yeah, a nice way to twist the arms kind of naturally is where is it? Is to twist the arms in the direction of from the elbow to the center of the circle. Gives them a natural twist a bit. Okay. Yeah. Oh, yeah. And then I've placed the elbow at the bottom here, so I've placed it at the negative up vector. All right. So let's actually make it function. Let's set the C-frames of the parts. So for the upper arm, we're going to want to set its C-frame from where? From the shoulder, looking at the elbow. And then for the lower arm, we want to look from the elbow to where? The wrist. That's the wrong button. Right. Okay. So we're almost there. What we have to do is we have to shift this arm forward by half of its size, and we have to shift this arm forward by half of its size. All right.
100,000 Robux are yours.
Not quite. I wish. But yeah, this case, I think when people do inverse kinematics on Roblox, they kind of leave it here because it looks good enough, and usually the characters are blocky anyway that you kind of don't see. Like, okay, so for instance, if I put his arm behind his back, uh, it definitely just broke. Like his arm, he broke some rotary cuff. But if I put it behind his back, it still looks okay without the context of I just broke his arm. But yeah, so this looks good like 90% of the time. But we can do a bit better. And specifically, what we can improve on is the position of the elbow. I mean, we have a whole circle of positions to use. Uh, we can do a bit better. And the idea that I'm using so the source of this comes from another Roblox developer named Axis Angle, and his idea. Let me demonstrate this. So this purple part here is supposed to indicate sort of like a natural resting position of the shoulder. And we're to find the position of the elbow on the circle, we want to start here at this natural position and find the minimum angle needed to rotate from the natural position to the circle. Kind of the philosophy there is like humans, we want to minimize energy when we perform movements. So we want to start from some natural position and move minimally to find an elbow position on the circle. Right. So I didn't prepare this part. This comes from the work I'm doing for the bounty. Actually, let me show you this. So this is where I'm at right now on the bounty. The legs look uh, decent enough, but the arms could use some work. Yeah, so we can kind of put his arm behind his back. It's okay. Um,
The most
but I'm actually
the most entertaining setup in VR is when you put the handsets down. When you take the headset off and you put the controllers down, and you look like you've become completely crumpled and destroyed in the world. I don't know if you can
yeah, I
solve
know
that
what you
problem.
mean. Hopefully, yeah, I think we can solve it. But okay, so this guy here is kind of showing what I was showing in the other thing of like we start at some natural resting position for the arm, and then we move it, we place the elbow a minimal amount of angle away. And I'm doing the same thing for the legs too. I think we should be able to adjust this on the fly. Oh God. That doesn't look so good. But yeah, maybe we can. Oh yeah, we can.
The orientation of the lower leg just completely reversed there somehow, right? That's interesting.
Yeah. So okay, so actually, let me explain to you a little bit of what the video I showed earlier that Ben had done. Other Ben. Okay, so this circle in the back is describing many different like natural leg positions. Or no, it's not quite that. So it's like when the shoulder is pointed at this particular at one of these points, each point describes an angle around the circle. So we're saying we're taking a weighted sum of uh, these angles. So depending on where your shoulder is looking at, it tries to find sort of a best angle by doing a weighted sum of these predetermined angles. So okay, I wish I had like a better visual than this image, but uh, so like if you look at this red part up here, if your shoulder is looking in the direction of that red, if that of that red part, we want to favor the angle that it describes. But if it's like between a few of these points, we want to. Did I say weighted? Maybe like average. We want to average them. Okay. Maybe it would help if I drew out what I was about to do. So what we have right now is this is the center of the shoulder. This is our circle of intersection, and we kind of have this like cone of vectors of what the shoulder could be. And then we also have this vector out here. This is like the default resting position of the arm, and we want the minimum angle to sort of map this onto the circle. And the way we're going to do that is with an axis angle rotation. So this is the center of our circle, and we have a vector here, and we want to rotate this orange vector to the blue vector by this angle. Okay, that's a bit messy. Okay, does that make sense though? So we're rotating the center of the circle towards what we consider to be the natural rotation, and we're doing it this alpha amount. Okay. All right. So how do we do this? I need to find it in my code. Okay. So we will consider the sort of the natural resting position. So we'll call this the base shoulder vector. So that's going to be the look vector of this part here. So I'll call this the base shoulder. It's going to be the base shoulder's look vector. And then we also want the vector here, this orange vector, to the center of the circle of intersection. So that's going to be, let me think, that's the center of the circle minus the shoulder. And then we need the axis to rotate about. So if we look at, okay, let me just pull them out here. We have these two vectors. The axis that we want to rotate, this orange vector to the blue vector, is going to be the one that's perpendicular to both of them. And I think I might have that upside down. It might be this one, but anyway, the vector that we want to the axis is going to be perpendicular to both of them. And to do that, we're going to use a cross product.
Yeah, the way you drew the rotation, that would be the correct orientation down.
Down? Okay. So then in that case, it would be two circle cross base shoulder vector.
I did not know
And
cross
then,
products were in in Roblox. Okay, that's useful.
oh my. Yeah.
I guess I should have assumed as much, but that's good.
Let's see. And then the angle that we want to rotate is going to be, so we have the circle. It's going to be the angle from here. Oh my. That. And let's see. It looks like I've done for this an arctangent. So we have this measurement here. We have that length, and then we also have this radius length. So the angle is just going to be an arctangent. Is that right? No, it's the length to the circle. Okay, and then that places the elbow. Right, we start from the shoulder, and then we want uh, an axis angle rotation. And the vector that we're rotating is right, it is the two circle vector, I believe.
What funny kind of thing is this dot from axis angle? It's not a property, it's a function. But why is it?
Yeah, it's a constructor.
Oh, okay.
So we've rotated it, and then to get back onto the circle, we need the length of, multiply that by the length of the upper arm. Okay, let's pray. What did I do? Line 60. Oh, it doesn't exist anymore. Wow, I'm okay. I'm really glad that worked the first try. But yeah. So you can see that the elbow is kind of near in the direction of this purple vector. And if we move the arm around a bit, it looks a bit more natural. And you can, let's see if we go behind the back. The arm might be twisted, but it does a decent job. Okay, yeah. And so what I was saying earlier, like with what Ben is doing, is we have a lot of these purple vectors, and we're averaging them uh, to kind of determine the best orientation for the elbow.
I still don't really understand what that means. Why are you not just sort of taking the nearest one, or what is, I don't know, when do they get averaged? If you just average them as vectors, you just get 0 at the center of the circle or something.
Right. I don't think I'm explaining this well. So it's not that we're averaging like the vector itself. So it's like what we're saying is when the arm is in this orientation, we're assigning it a certain angle around the circle. So like separate from what we're doing right now, like ignore what we're doing right now. When the arm looks in this direction, we want to assign it an angle around the circle. And when the arm looks in some other direction, we want to assign it some different angle around the circle. And so depending on where the arm is, we want to average these angles. Well, so the reason it's like useful is because we can say that when the arm looks in this way, we can predefine like what a good rotation is, what a good position for the elbow is. And when the arm looks in this direction, we can predefine what a good elbow is there.
Is it basically you just want near each of those predefined vectors it to basically do what you're describing and to smoothly interpolate between them as the arm switches from one to the other? Is that the reason for this?
Yeah.
Yeah, okay. Then I understand. And it's just, there's some way of doing that interpolation and who cares, but that's what you're trying to achieve.
Exactly, yeah.
Okay.
Okay, that's all I have. I'd give you back 8 minutes. I can also show you. Well, okay, let's end it here.
Yeah, thanks a lot. That was great.